Imagine you're drifting weightless through the endless dark of space. All around you is silence, vast, black, and infinite, broken only by the scattered glow of distant stars. Then, suddenly, a vision appears ahead, unlike anything you've ever seen. A radiant blue ring, slender yet impossibly perfect, as if some cosmic hand had drawn it with a giant compass. Inside that ring glows a golden heart, warm and ancient, like the lantern of a civilization that fell asleep billions of years ago. It's no illusion, no artist's rendering. It's real, a galaxy quietly floating more than 600 million light years away, its light beginning its journey long before humans ever walked the Earth. Astronomers call it Hoag's object, and the moment you look at it, you might feel what they felt, wonder mixed with disbelief. The universe is famous for chaos. Galaxies twist, collide, tear apart, and stretch under the pull of their massive neighbors. Even the most graceful ones usually hide tiny flaws, a spiral arm out of step, a thin dust lane slashing across the core, a faint scar left by some ancient collision. But Hoag's object seems to ignore all that. It's too round, too symmetrical, too serene to have simply emerged from the cosmic turmoil. When the first photo of this galaxy was taken in 1950, its discoverer, astronomer Arthur Hoag, could hardly believe he'd found something truly new. At first, he thought it might be a planetary nebula, the glowing shell of a dying star. But as better telescopes came along, that idea fell apart. This wasn't a fading cloud of gas. It was a massive galaxy with an old golden core surrounded by a brilliant, youthful blue ring, separated by an oddly empty gap. And most astonishing of all, there's no evidence it's ever been smashed, torn apart, or violently reshaped. The kind of cosmic drama that usually builds galaxies. Its very shape challenges everything we thought we knew about galaxy formation. A flawless blue ring wrapped around an ancient yellow center, divided by a strangely clean void, as if some invisible force had gently split the two and kept them apart. Its near-perfect symmetry feels less like random gravity and more like intentional design. It looks like abstract art painted across the cosmos. That's why Hoag's object has puzzled astronomers for more than 70 years. Countless theories have tried to explain it, from galactic collisions and gravitational resonances to cold gas accretion and the hidden hand of dark matter. Yet none fit completely. Each explains a piece of the puzzle, only to fall apart under the next detail. In a universe that thrives on imperfection, Hoag's object stands as a breathtaking paradox, one that challenges human understanding and refuses to let go of our curiosity. Today, we'll dive into the strange story of this mysterious galaxy, explore how it seems to defy the rules of galactic evolution, and uncover why, even after decades of study, Hoag's object remains one of the most beautiful unsolved mysteries in the universe. On a quiet night in 1950, at the Palomar Observatory in California, astronomer Arthur Allen Hoag was carrying out his usual sky surveys. He wasn't hunting for strange cosmic phenomena or rare galaxies. His job was more routine, taking wide-field optical photographs to study stars and other celestial structures. This was long before the heavens had been combed through by giants like Hubble or by computers capable of processing billions of points of light. Hoag had only a 48-inch Schmidt telescope and fragile glass photographic plates that had to be chemically developed, then carefully measured by hand with rulers and magnifying lenses. In that era, astronomy leaned heavily on patience and the sharp eyes of the observer. Among thousands of faint, blurry specks, Hoag suddenly noticed something odd, a perfectly round glow, with a bright core in the center and a hazy ring around it. At first, it didn't seem like anything extraordinary. Planetary nebula, glowing shells of gas expelled by dying stars, often appeared as neat circles. A faint ring with a bright middle? That fit the familiar pattern. Hoag dutifully noted it down, filed the object away in his catalog, and moved on. But the image stayed in the back of his mind. Something didn't feel right. The ring looked too wide, too luminous compared with any planetary nebula he knew. The core didn't resemble a single dying star. It seemed denser, more like a cluster or a tiny galaxy. Yet in 1950, Hoag had little means to dig deeper. Tools like modern spectroscopy or space telescopes were still out of reach. Back then, science was often an educated guess built on grainy black and white photos. Even so, Hoag published a short paper describing the object as an unexplained ring structure, perhaps a nebula. perhaps some unusual galaxy. The paper drew little attention. It was just one small puzzle among countless sky surveys of the time. But from that modest note, a quiet mystery began. Over the following years, Hoag's image caught the eyes of other astronomers and sparked curiosity. Most galaxies humans knew then were either spirals with messy arms or ellipticals with featureless light. Perfect circles were almost unheard of, and when rings did exist, they were usually warped by collisions and turbulent gas streams. Yet in Hoag's photograph, the outer ring appeared clean, symmetric, and flawless, as if drawn with a cosmic compass. Some even wondered if it might be a photographic glitch or an optical illusion. But no one had solid proof either way. The real turning point came in the 1960s and 70s when astronomy entered a new era. Larger telescopes, electronic detectors, and especially spectroscopy. The art of splitting light into its wavelengths changed everything. By analyzing light's fingerprint, scientists could measure a galaxy's distance, speed, chemistry, even age. When they finally applied these tools to Hoag's mysterious ring, the results stunned them. This was no nearby planetary nebula, but a massive galaxy nearly 600 million light-years away. In other words, the light Hoag captured had set off across the universe long before complex life existed on Earth. That revelation instantly elevated the discovery. A strange nebula is one thing, but a fully formed, nearly perfect ring galaxy is another. Most ring galaxies we know are born from violent collisions, leaving them warped and messy, full of stellar debris and chaotic gas. But Hoag's object, as the community now called it in his honor, looked serene, tidy, untouched by violence. And yet, for decades, Hoag's object stayed in a scientific gray zone, intriguing but poorly understood, limited by the blurry view from Earth's atmosphere. We knew it was a galaxy, but its exquisite shape remained a misty enigma. Everything changed in 2002 when the Hubble Space Telescope turned its razor-sharp eye on Hoag's object. For the first time, humanity saw it in breathtaking detail. A smooth golden core, perfectly round, surrounded by an empty black gulf, then an electric blue star-forming ring glowing with youth. No dust lanes, no spiral arms, no visible scars of violence. It was stunning. Not just artistically beautiful, but too perfect compared with our messy theories of how galaxies form and evolve. From that moment, Hoag's object became a cosmic celebrity. Hypotheses about its origin surfaced and fell apart one by one. Every detail in the Hubble image, the symmetry of the ring, the ancient core, the eerie void between, whispered new questions. How can a galaxy remain so calm and complete in a universe built on collisions and chaos? Why is its core so old, while its ring blazes with young stars? What holds such a delicate structure together for hundreds of millions of years? From a faint smudge on Arthur Hoag's photographic plate, this galaxy grew into one of the great riddles of the cosmos. It's a testament to the power of curiosity and chance discovery. How a careful glance at an ordinary image can open a new chapter in science. And more than half a century after that night at Palomar, Hoag's object still challenges astronomers to ask the most fundamental questions. Do we truly understand how galaxies are born, grow, and transform? Or might the universe still hold unseen mechanisms, waiting for another curious gaze, like Hoag's, to reveal them? If there's one detail that makes Hoag's object instantly breathtaking the moment you see it, it's the deep blue ring wrapping around the galaxy. It's not just beautiful, it's strange in a way that feels almost defiant of logic. Even from more than 500 million light-years away, the ring is impossibly clear. A thin, smooth, perfectly even band of soft blue, as if someone had drawn it with a single, flawless brushstroke. Perfect curves are almost non-existent in the universe. Gravity from billions of objects, from lone stars to neighboring galaxies, usually pulls, stretches, and tears structures into chaotic shapes. And yet, here it is, a young stellar ring so precise it forces scientists to ask, how could the universe make something this exact? That outer ring is made of millions of young stars, most only a few 100 million years old, practically newborn compared to the age of the cosmos. Young stars glow blue because they burn hotter and brighter than our sun. That's why, when the Hubble Space Telescope first zoomed in on Hoag's object, the ring popped out in a cool, icy blue, starkly contrasting with the golden, aging core at the center. It's a sign that the ring is still forging new stars, a quiet nursery of life floating in the dark. What's most puzzling is its almost perfect roundness. Galaxies with rings are rare, but even the few we know usually look warped. The ring might be stretched into an oval, broken into uneven segments, or sprouting spiral arms that don't quite close. Collisions, the most common way to make ring galaxies, usually leave behind scars. Long tidal tails, streams of scattered stars, or dusty arcs twisted into strange shapes. But Hoag's object is different. There's no tidal tail, no chaotic debris, no dusty bridge linking the ring to the core. Its circle is closed and clean, seamless from start to finish, as if it's never been shaken by cosmic violence. Astronomers have hunted for even the tiniest imperfections, because usually no galaxy is flawless. You can spot subtle scars, thicker spots, thinner gaps, brighter arcs, or faint wisps of matter if you look closely enough. But Hoag's object doesn't seem to have any. Its ring keeps a nearly uniform thickness, and its brightness is distributed almost perfectly all the way around. This makes it an accidental gold standard. Researchers who test image processing algorithms sometimes use Hoag's object itself. It's so round and smooth that if your software detects distortion, odds are the code is wrong, not the galaxy. The stability of this structure gets even more mysterious when you think about the galaxy's internal dynamics. A ring of young stars shouldn't just stay neat on its own. Something has to be balancing it. Those stars are whipping around the core at incredible speeds, and over time, even tiny disturbances should stretch, ripple, or warp the ring. In most galaxies, collisions or incoming streams of gas eventually break this balance, spawning spiral arms or breaking the ring into fragments. But in Hoag's object, it's as if some invisible hand, maybe a perfectly smooth halo of dark matter, is keeping everything in check, holding the ring in a near-ideal orbit. The ring's blue color isn't just pretty, it's a scientific clue. Blue means the stars are young and hot, which means star formation is still happening. To make new stars, the ring must contain huge amounts of cold hydrogen gas as raw material. But here's the paradox. When astronomers look with radio and infrared telescopes, they see surprisingly little turbulence or inflowing gas around the ring. It's almost eerily calm, unlike the chaotic, stormy environments where stars usually form. So where did the gas come from? And how could it quietly build this young, vibrant ring without leaving behind any evidence of violence? One theory says the ring formed when a small galaxy passed straight through the larger one, sending out a shock wave that compressed gas into new stars, a process known as a collisional ring. But with Hoag's object, there's no trace of such an intruder. No leftover debris, no stretched orbits, no stars flung outward. Another idea suggests the ring came from gravitational resonance, where a central stellar bar stirs up orbits and funnels gas into a circle. But Hoag's object's core is smooth and unbarred. That theory doesn't fit either. Some scientists propose the ring may have formed from cold gas accretion, primordial gas slowly raining in from intergalactic space to build a new ring. But that usually creates messy, lopsided structures, not a pristine circle like this. Others wonder if an unusually smooth, dense halo of dark matter might be stabilizing the orbits of gas and stars, keeping the ring perfectly round. But that's still speculation. No one has been able to confirm such a halo exists. The ring also raises questions about its age. If it's been around for a long time, it should have started to warp or fade. If it's new, its birth should have left obvious traces, but telescopes haven't found any. It's like looking at a freshly painted masterpiece. Pristine, untouched by time, but no one knows who painted it or how. Because of this strange perfection, the blue ring of Hoag's object has become a symbol of everything we still don't fully grasp. It makes us wonder, are the rules we use to describe galaxy formation just incomplete sketches? Could there be gentler, rarer evolutionary paths out there, so uncommon they appear only a handful of times across the vastness of space? That silent blue ring circling an aging golden core also stirs something deeply human, a sense of fragile balance. In a universe where collisions and chaos are the norm, Hoag's object feels like a fleeting miracle, a moment of order amid endless turmoil. It makes you pause, take a breath, and reflect. Even in the harshest places, the cosmos can craft something delicate and perfect, as if to remind us we still don't know all the ways it can surprise us. For astronomers, this isn't just a pretty picture. It's a natural laboratory, a place to test ideas about dark matter, star formation, and galactic dynamics. Every new observation, from its light spectrum to its rotation speed to the distribution of its gas, is another puzzle piece in a picture no one has finished. And maybe that's exactly why this near-perfect ring is so hard to explain. It's too clean, too well-behaved to fit neatly into any familiar theory, forcing scientists to keep thinking bigger and to imagine paths the universe might take beyond the ones we already know. So when you look at Hoag's object, you're not just admiring a galaxy painted in cosmic blues and golds. You're staring at a living mystery, a challenge to everything we think we know about how the universe builds its worlds. And that flawless blue ring, quietly spinning in the dark, might be the universe's gentle but steadfast reminder. There are still countless secrets waiting to be uncovered. If the blue ring of Hoag's object feels like a bold, fresh brushstroke, vivid and youthful, then its golden heart at the center is something else entirely, an ancient core that seems to have been beating quietly for billions of years. When you look at the Hubble image, it's hard not to be drawn to that soft yellow glow. It's not dazzling or razor sharp, but it radiates a gentle, warm, almost weary light, like a sun that left its youth behind long, long ago. While the outer ring is energetic and alive, the core feels calm and timeless, like a silent witness wrapped by a halo of newborn stars. The core itself is a smooth, softly elliptical shape with almost no visible structure. If you look at spiral galaxies like our Milky Way, their centers are often tangled with dusty lanes, faint swirling arms, or even a bright central bar of stars. But Hoag's object is different. Its heart is strikingly clean. No bar, no spiral arms, no dusty filaments winding inward. Just a seamless sphere of golden light, polished smooth by billions of years. This cleanliness is surprising. It suggests a history of astonishing calm, or at least the absence of any violent disturbance for an extraordinarily long time. Most of the stars in this core are cosmic veterans, ancient, long-lived, and quietly aging. Spectral studies show they were born billions of years ago, when the universe itself was far younger. Their yellow glow comes from stars that have cooled over time, burning through much of their hydrogen and moving into late stages of stellar evolution. They're no longer the hot, blue, high-energy stars you see in the outer ring. Instead, they shine with a steady, mellow warmth. This tells astronomers that the core was once an old, mature galaxy that long ago stopped forming stars, growing old in silence, while out beyond, an entirely different story began. One of the strangest things about this golden heart is how dynamically separate it is from the outer ring. In a normal spiral galaxy, the rotation of the core and the outer disk are linked. The core can shape the orbits of the stars outside, sometimes creating bars or spirals as their speeds differ. But in Hoag's object, measurements show the core rotates slowly and almost independently, while the blue ring spins swiftly and cleanly around it. It's as if there are two systems living side by side, each following its own rules, coexisting but not deeply interacting. This raises a big question. Was the ring formed long after the core had grown old? Or were these once two separate galaxies that somehow merged with extraordinary gentleness? The smoothness of the core is another piece of the puzzle. Most galaxies bear scars of past collisions, stretched streams of stars, warped dust lanes, or at least some asymmetry in their shape. Collisions and mergers are how galaxies grow and change. A smooth, round core usually means past mergers, but such events rarely happen without leaving behind chaos. If Hoag's object did merge in its past, it must have happened in a way so delicate and balanced that it barely disturbed the galaxy's form. Spectroscopy adds more intrigue. The core's light shows it's metal-rich, a sign of long, repeated star formation in the distant past. When old stars die and explode, they seed space with heavy elements, enriching the next generations. In contrast, the outer blue ring's stars are metal-poor, hinting their gas might have come from somewhere beyond the original galaxy. These two chemical portraits support the idea that the core and the ring belong to entirely different evolutionary eras, maybe even different galactic stories that somehow merged into one. Another striking feature of the Golden Heart is its quietness. Radio and infrared telescopes find little gas or dust inside. There's no sign of active star birth, no fresh streams of gas feeding the core. It's as if the star-forming engine has completely shut down. Meanwhile, the outer ring is alive with stellar nurseries. Between them lies a vast empty gap, like a cosmic buffer zone separating a silent past from a vibrant present. This contrast forces astronomers to wonder, how did two parts with such different histories end up fitting together so perfectly? If the ring formed later, why didn't its birth distort the core or pull it into a bar? If these were once two galaxies, how could their union have been so peaceful? And if this is one galaxy evolving through different eras, what made the center fall dormant while the outer regions burst back to life? Some astronomers propose that the core might be the fossil of an ancient elliptical galaxy, one that formed and aged in solitude, then later captured a fresh supply of cold gas from its surroundings. Instead of falling straight into the core, that gas may have settled into a stable outer orbit, creating today's youthful ring. But why didn't the gas crash inward and restart star formation in the core? Perhaps Hoag's object's dark matter halo acted like a gravitational fence, keeping the gas at a distance, but that's still speculation. Another idea is that the core once merged gently with a smaller galaxy, stripping the intruder of its gas to form the outer ring. If the merger was slow and quiet enough, it could have spared the core from damage, leaving it round and smooth. But mergers this calm are rare, and so far, astronomers haven't found clear traces of such an event here. What makes this golden heart so captivating is its silence amid youthful chaos. It's like an ancient city frozen in time, surrounded by a glowing, expanding modern metropolis. No smoke, no construction, only the quiet glow of old stars shining one last time. The image is haunting and beautiful, reminding us that cosmic structures grow old too, and that the new and the ancient can exist side by side without ever touching. From a scientific view, Hoag's object's golden core is a key to unraveling the galaxy's mystery. It carries the memory of ancient star formation, possible mergers, and the cosmic environment over billions of years. Yet it also poses paradoxes. Why is it so old and undisturbed while youth and energy bloom around it? Why hasn't it been pulled into the ring's story? And what kept it so smooth and pristine when other galactic cores grow tangled and complex? Gazing at this quiet heart, you can almost feel time itself, vast and unhurried, flowing through it. Its stillness makes the vibrant blue ring seem even more alive, and it turns Hoag's object into a galaxy unlike any other. It's a reminder that the universe doesn't always follow simple rules. Sometimes, ancient relics and fresh beginnings can share the same space in perfect, improbable balance, leaving science humbled and wondering if we truly understand how galaxies are born and change across cosmic time. If the bright blue outer ring of Hoag's object is a youthful, radiant crown wrapped around an ancient golden heart, then the space between them is its most haunting feature. In Hubble's image, this gap looks like a perfect cut, pitch black and utterly still, slicing apart two opposing worlds. No faint bridges of starlight, no drifting dust, no lonely stars crossing the void as they often do in other ring galaxies. It feels like a moat around a timeless fortress. Beautiful, yet cold, empty, yet whispering a story no one has decoded. In the cosmos, empty space isn't rare. Many galaxies have star-poor regions near their centers or edges, shaped by gravity, collisions, or slow evolution. But a gap as wide, symmetrical, and pristine as Hoag's objects is another story. Usually, the area between a galaxy's core and its ring still holds leftovers, old stars from the original disk, streams of disturbed gas and dust, or at least a few drifting clusters. Modern telescopes, sensitive to the faintest light, almost always spot some trace of past activity. Yet repeated observations confirm that Hoag's object's gap is nearly, shockingly, bare. And it's not just empty of stars. It's empty of gas and dust, the raw ingredients for making new ones. That suggests star formation there shut down long ago, or the region was swept clean in some dramatic event. Picture the galaxy as a city, its golden core, an old downtown, its brilliant blue ring a lively suburb. The gap would be a deserted belt of land. No streets, no homes, nothing but silent ground between eras. One idea proposes that the stars and gas in Hoag's object settled into orbits that naturally forbid material from lingering there. In space, orbital dynamics can create no-go zones, where gravity and rotation combine to sweep matter away like a cosmic racetrack. Anything entering gets flung out or forced onward, leaving behind a natural void. If true, this gap could be the product of perfect dynamical balance, a place where anything trying to stay is inevitably pushed aside. But there's a problem. To carve such a wide, perfectly round forbidden zone, the system would need almost unreal precision. Other galaxies with gravitational resonances forming gaps rarely look so immaculate, and they're usually supported by a central bar to maintain the resonance. Hoag's object has no bar, so while the orbital stability idea works in theory, it doesn't explain how such a flawless gap could have formed. Another hypothesis suggests the region was once filled with material, but later swept out by a powerful event. Perhaps long ago, the galaxy's core flared as an active supermassive black hole, feeding furiously and blasting out winds and radiation strong enough to blow away gas and dust. This process, known as AGN feedback, is seen elsewhere, where violent outbursts clear central regions and halt new star birth. If Hoag's object went through such a phase, it might have emptied its inner ring before calming down. Yet there's no clear evidence for this. Hubble and X-ray telescopes haven't spotted the telltale signs of an active nucleus. If the black hole once raged, we'd expect leftover bubbles of gas or other energetic scars. Their absence suggests that if it happened, it was so long ago that nearly all traces have faded. Some scientists imagine a gentler but highly efficient merger instead. In this scenario, a small, ancient galaxy once slipped quietly into Hoag's core, disturbing the inner material and pushing it outward, leaving a ring-shaped desert. Later, fresh gas, perhaps drawn from intergalactic space or the swallowed companion, settled at the outskirts and formed the youthful blue ring. This would explain the age gap between core and ring and the empty space between them. But again, there's a snag. Mergers usually leave footprints, tidal streams, scattered debris, dusty plumes. None have been seen. What makes this void stranger is its astonishing cleanliness. Deep radio and infrared observations, sensitive to cold gas and dust, find almost nothing. In most galaxies, even seemingly dark areas hide atomic or molecular gas, or stray old stars left behind by evolution. Hoag's object defies that rule. Its gap is so dark and bare that astronomers use it as a baseline when measuring the outer ring's brightness. Aesthetically, the effect is breathtaking. The galaxy looks like a flawless piece of cosmic design, golden core, turquoise ring, and between them a crisp black divide, as if someone outlined two worlds by hand. In a universe where chaos is the norm, such neat separation feels like a quiet act of rebellion. I refuse to be messy. For scientists, the void isn't just striking. It's a crucial clue to the galaxy's origin. It holds the history of how Hoag's object came to be. If it was cleared by a black hole, what does that reveal about its ancient activity? If it's the product of orbital resonance, what does that say about the galaxy's dark matter and gravitational field? And if it's the remnant of an exceptionally gentle merger, how could the universe choreograph such a graceful dance without leaving scars? Some go further, proposing wilder ideas. Perhaps the gap was once an old stellar disk slowly devoured by the core, or it dissolved due to exotic gravitational interactions with an unseen dark matter halo. Studying the dynamics of this region might even help test alternative gravity theories, like MOND, which tweaks how we think gravity works on galactic scales. Philosophically, the void feels poetic. It's like a pause in music, a silence that makes the youthful outer melody and the ancient inner baseline more profound. It's a temporal border, separating the cooled past of the golden heart from the thriving present of the blue ring. Its emptiness might be the fossil trace of a cosmic turning point, the moment the galaxy chose a new path. To casual stargazers, Hoag's object looks like a floating ring in the dark. To astronomers, it's a puzzle, too perfect to be chance, too clean for familiar collision stories. That silent black moat may hold the key, a record of a hidden merger, a long sleeping black hole's outburst, or an exquisitely tuned gravitational dance the universe rarely performs. When people admire Hoag's object, their eyes go to the shimmering blue ring or the warm golden core. But it's the eerie, immaculate gap between them that makes this galaxy unforgettable. It's the loud silence in the cosmic symphony, a silence every scientist longs to hear clearly, hoping it will whisper how galaxies are truly built and transformed over billions of years. In astronomy, when a galaxy shows off a brilliant ring of young stars wrapped around an ancient core, Scientists usually have a few go-to stories to explain it. But with Hoag's object, every familiar script falls apart. Its blue ring isn't just beautiful and perfectly round, it defies every theory that's worked for dozens of other ring galaxies. The question, where did this blue ring come from, has turned into a theoretical maze, where every seemingly reasonable path ends in a dead end once the data is examined closely. The first and most common idea is a galactic collision. When a small galaxy plunges through the disk of a larger one, gravity and shock waves can fling material outward, compress gas into new stars, and form a ring around the core. We've seen galaxies like this. The famous Cartwheel Galaxy is a dramatic example. Its glowing ring born from a cosmic crash. Such events usually leave unmistakable scars. A warped core, long tidal tails stretching into space, scattered debris, and streams of stars pulled like threads. But Hoag's object has none of that. No tails, no faint star halo, no shredded dust. Its core is suspiciously round and smooth, and the ring is nearly perfect. If there was a collision, it would have to be the gentlest in cosmic history, mild enough to leave no trace, yet somehow powerful enough to create a star-forming ring tens of thousands of light-years wide. It sounds contradictory. The second idea leans on gravitational resonance, a familiar mechanism in spiral galaxies. Many galaxies have a central bar of stars, and the bar's rotation can create resonances that pile up material into circular or elliptical rings at certain distances. This explains many inner and outer rings in disk galaxies, from tiny dusty loops near the core to large star-forming rings farther out. But Hoag's object doesn't have a bar or any sign of spiral structure. Its core is a smooth, featureless ellipse with no elongated bar to stir up resonances. Without a bar, it's hard to see how a stable, round ring could form or persist. Some astronomers turn to a third scenario, cold gas accretion from the intergalactic medium. In this picture, an aging galaxy slowly siphons cool hydrogen from the space around it. As the gas settles into certain orbits, it condenses and forms new stars, creating a fresh ring. This sounds reasonable, especially since Hoag's blue ring is clearly birthing young stars. But computer models of cold gas accretion usually produce messy, lopsided structures because infalling gas comes from many directions, colliding and swirling chaotically before calming down. To get a nearly perfect circle, the gas would need to be guided into orbit with an impossible level of symmetry. On top of that, observations haven't found streams of gas feeding in, and the hydrogen halo around Hoag's object seems too calm for such an active refueling process. The fourth, and to some astrophysicists the most intriguing, idea involves dark matter. Every galaxy sits inside a massive, invisible dark matter halo that shapes its gravity. If Hoag's halo were unusually smooth and perfectly balanced, it might create a stable gravitational field that shepherds gas and newborn stars into a flawless orbit. Some simulations show this could happen, but achieving Hoag's level of perfection would require an almost ideal halo, undisturbed, symmetrical, and free from the warps and clumps caused by past mergers. The problem? Most galaxies have collided or merged at least a little, leaving their halos messy. Hoag's object looks too clean, hinting we may not fully understand how dark matter shapes galaxies. Beyond these main ideas are bolder speculations, none with solid proof. Some scientists imagine an ultra-gentle merger, a gas-rich dwarf galaxy slowly dissolving into Hoag's outskirts, feeding the ring without disturbing the core. It's elegant, but nearly impossible to verify, since such scar-free mergers are rare and hard to simulate. Others suggest ancient gravitational waves from some long-gone cosmic event could have stirred the halo's gas into a ring. A beautiful notion, but practically untestable with current data. A few even picture Hoag's object patiently drawing in intergalactic material in a perfectly balanced billion-year dance, like an artist sketching an immaculate circle, stroke by stroke. Yet again, no direct observations show such inflows. What makes Hoag's object so frustrating and fascinating is that each theory explains part of the picture, but not all. Collisions can trigger star formation, but not this eerie symmetry or lack of debris. Resonances can sculpt circles, but there's no bar to drive them. Cold gas could bring fresh fuel, but not in such silence and perfection. Smooth dark matter could maintain the orbit, but we've never seen a halo so ideal. The wilder ideas are either unprovable or beyond our current instruments. This isn't just a geometric puzzle, it touches the heart of how galaxies grow and renew themselves. If Hoag's object built its blue ring in a way we've never imagined, it means the universe has more evolutionary strategies than we thought. It hints that, beyond violent crashes and chaotic gas inflows, there might be slower, subtler forces capable of sculpting something this perfect. Hoag's object is also a stress test for cosmological models. Every time scientists simulate galaxy formation, they check whether their virtual universes can create real galaxies. But Hoag's nearly always breaks the simulation. The rings come out warped, uneven, or littered with debris. No one has made a perfect circle like Hoag's without tweaking parameters to unrealistic extremes. That makes it a powerful benchmark. If your model can't produce Hoag's object naturally, maybe it's missing something fundamental. For many astronomers, this mismatch is the most exciting part. A galaxy this perfect could hold keys to big questions. Have we misunderstood dark matter's role? Are our current gravity laws enough to explain galactic dynamics? Could galactic refueling processes be more delicate than we think? Hoag's object acts like a natural laboratory, pushing scientists to test new ideas, from exotic dark matter halos to tweaks in large-scale gravity. But beyond the equations and models, the mystery of its blue ring strikes a deeper, more human chord. It reminds us the universe still has secrets, beautiful outliers that challenge our confidence. We like to believe we've mapped the rules, that our theories can explain it all. And then, suddenly, a flawless galaxy appears, as if to smile mischievously and whisper, "Not quite yet." That's why the story of Hoag's object isn't just dry astrophysics. It's a reminder that science thrives on what we don't understand. Each failed hypothesis isn't defeat. It's a step closer to seeing the universe's richness. And maybe the ring's impossible symmetry, its serene perfection amid cosmic chaos, is the universe's gentle way of telling us there's still so much left to learn, and that wonder itself is a reason to keep looking up. One of the most puzzling things about Hoag's object is the strange age gap between its two main parts. The outer blue ring looks fresh and full of energy, while the golden core at the center feels like an old photograph faded by time. They seem like two worlds that don't belong to the same story. Together they form a nearly perfect shape, yet their histories don't line up at all. The age difference is so extreme that many astronomers have asked, are we really looking at one galaxy or two galaxies wearing the same cosmic shell? To understand why this is so odd, we need to look at how galaxies usually grow old. When a galaxy is young and full of gas and dust, it goes through bursts of star formation. Hot, bright blue stars appear in great numbers, giving the galaxy a vivid bluish glow. Over time, that gas gets used up or blown away, star birth slows down, and the galaxy becomes older and redder as long-lived yellow and red stars take over. Without a new supply of cold gas, the galaxy dies slowly, fading into a quiet, golden elliptical shape. This process tends to be fairly smooth. The inner regions usually age first, while the outer parts might stay a little younger, but still follow the same timeline. Hoag's object completely breaks that script. Its core is the textbook image of a galaxy that burned through its fuel long ago. Spectral analysis shows that the stars there are billions of years old and rich in heavy elements, proof of many generations of stars that lived and died. There's no cold gas left to make new stars. The yellow core is in a state of deep hibernation, glowing faintly with the warm light of aging suns. It's exactly what we'd expect from an ancient, quiet, elliptical galaxy. But the outer ring is shockingly young. Most of its stars are only a few 100 million years old, cosmic teenagers compared to the 13 billion year history of the universe. Their vivid blue color means star formation is happening right now. Astronomers have also detected cold hydrogen gas in the ring, the raw fuel for future stars. In other words, the outer region of Hoag's object is alive and busy making new suns, while the center gave up long ago. This age gap has baffled scientists for decades. If Hoag's object were a single coherent galaxy, why would there be such a clean break between an ancient silent core and a youthful star-forming ring? Normally, if a dead galaxy gets fresh gas, that material falls toward the center first, where gravity is strongest, rejuvenating the core before the outskirts. But here, the opposite happened. The center stayed asleep while the outer edge lit up with new life. Several ideas have been proposed to explain this cosmic mismatch. 1. A refueled ancient core. The leading theory suggests the yellow center is an old elliptical galaxy that later captured a massive supply of gas from its surroundings. But instead of falling inward, the gas settled far away, forming the blue ring. Something, perhaps the galaxy's dark matter halo or unusual orbital dynamics, might have created a stable zone that kept the gas from collapsing into the core. If true, Hoag's object would be a rare case of an old galaxy rejuvenating only on the outside. The challenge is that astronomers haven't yet found clear signs of the infalling gas or debris from this process. 2. A gentle galactic merger. Another scenario imagines that the yellow core was once a lonely elliptical that slowly swallowed a smaller, gas-rich galaxy. As the smaller galaxy was stripped apart, its gas formed the outer ring. Because the merger was unusually calm and stretched over time, it didn't trigger the chaotic streams of stars or dusty wreckage we usually see after such events. This idea is elegant. It explains both the young ring and the old core. But the merger would have had to be extremely smooth, almost implausibly so. Most collisions leave behind at least some mess, yet Hoag's object looks suspiciously pristine. 3. Slow, quiet gas accretion. Perhaps the galaxy didn't get one big gulp of fuel, but rather sipped intergalactic gas bit by bit over billions of years. The inflowing material could have been trapped in the outer regions by rotation and the dark matter halo, building a stable ring without disturbing the core. This would be subtle enough to leave no obvious scars. But it requires an almost perfect balance, gas arriving steadily, not too much at once, not too little, and a halo smooth enough to keep everything in order. 4. A self-locked core. It's also possible the core sealed itself off after running out of fuel. When galaxies stop forming stars, their central supermassive black holes can blow out powerful winds that heat or expel nearby gas, preventing new material from falling inward. If Hoag's object once went through such a phase, its core could be permanently shut down, forcing any later gas to stay in the outskirts and form the ring. The problem is that we don't see strong evidence today of an active galactic nucleus in its past, so this idea remains unproven. No matter the explanation, every theory has to answer the same riddle. Why is there such a razor-sharp age boundary? It's as if the galaxy is split by an invisible knife, an ancient metal-rich heart inside and a young star-forming halo outside, with almost nothing bridging the two. Galaxies usually show smooth age gradients, but Hoag's object has a dramatic, almost binary contrast. The chemical makeup reinforces this story. The core is metal-rich, the byproduct of countless stellar generations. The ring is more metal-poor, hinting that its gas may be more pristine, either drawn from intergalactic space or from a small, underdeveloped galaxy. This strongly suggests the ring isn't just leftover material from the original galaxy, but something acquired later, or formed in a completely separate evolutionary phase. Some astronomers even joke that Hoag's object is like two galaxies sharing the same house, but never speaking to each other. Seen from a more philosophical angle, this mismatch turns Hoag's object into a metaphor for time itself. It holds deep cosmic memory and fresh creation in one frame, a golden heart full of ancient history, surrounded by a brilliant blue ring of youth. It's like an old city encircled by modern suburbs, history and renewal side by side, yet clearly divided by an invisible boundary. For astrophysics, this age paradox is a tough stress test. Most models assume some degree of continuity. Fresh gas should gradually rejuvenate a galaxy from the inside out, or mergers should leave messy evidence. Hoag's object refuses both ideas. It's an ancient core wrapped in a young ring, with no visible scars between. This forces scientists to rethink fundamental assumptions about how galaxies age and, in rare cases, find new life. And maybe that's exactly why Hoag's object is so fascinating. It's not just visually stunning, it's a cosmic challenge, hinting that there may be hidden evolutionary paths and delicate processes powerful enough to revive part of a galaxy while leaving the rest untouched. Every new measurement of its star's ages doesn't just add data. It sparks fresh questions, inspires new models, and reminds us how much we still don't know. When we look at Hoag's object, we're not just seeing a beautiful two-tone galaxy. We're looking at two timelines running side by side, a distant past and a youthful present, coexisting but strangely disconnected. That's what keeps astronomers both puzzled and enchanted. More than 70 years after Arthur Hoag first snapped a blurry photo of this object, it remains one of the universe's most elegant, unsolved mysteries. In most of the galaxies we know, especially disk-shaped ones, the centers are anything but calm. They often sport a stellar bar cutting straight through the core, a colossal highway of billions of stars, or elegant spiral arms stretching outward, creating that familiar yet chaotic beauty. These features aren't just decorative. They reveal how a galaxy moves and evolves. A bar acts like a gravitational expressway, funneling gas and dust toward the center to feed a supermassive black hole or spark new star formation. Spiral arms with their rippling waves of matter signal flows, collisions, and uneven distributions of mass. But look at Hoag's object, and all of that familiarity vanishes. No bar, no spirals, no tangled dust lanes, just a smooth, polished-looking elliptical core wrapped by a flawless ring of blue stars. This absence is more startling than it first seems. In the universe, bars aren't rare at all. About 2/3 of disk galaxies, including our own Milky Way, have one. A bar forms when the inner region rotates fast enough and mass is distributed just right to trigger gravitational resonance. It plays a key role in pulling material inward, fueling star formation, and keeping a galaxy active. When a galaxy has no bar, it usually means its structure is unusually stable, or its evolution took a very different path. But Hoag's object doesn't just lack a bar, it shows no hint that one ever existed. Its core is so clean and smooth, you'd think it had never experienced the internal turbulence needed to stretch stars into a bar at all. The same goes for spiral arms. Spirals are common in young or star-forming galaxies. They aren't fixed trails of matter, but density waves, temporary traffic jams of gas and stars flowing in and out, like congested lanes on a busy freeway. Spirals naturally arise from instabilities in a galactic disk and the complex pull of gravity between stars. That's why finding an actively star-forming outer ring without any spiral structure is almost unheard of. Normally, if the outer regions are busy making stars, spirals appear to organize the flow of material, or at least leave some asymmetric ripples. Yet Hoag's object is perfectly smooth. Its ring is an even, unbroken circle with nothing stretching inward. This strange simplicity raises a question. Is Hoag's object really a disk galaxy at all? Its central shape, a polished, featureless ellipse, looks more like an ancient elliptical galaxy than a spinning disk. Ellipticals are known for being quiet and structureless. They often form after violent mergers, when the original disk is destroyed and replaced by a chaotic, aging ball of stars with no gas left for new ones. But if the core of Hoag's object is an old elliptical, how did it end up surrounded by a perfect, youthful ring? That's the paradox, a heart marked by an ancient, violent past, wrapped in a halo of new life and delicate symmetry. Some researchers have suggested that maybe Hoag's object once had a spiral disk or a bar, but lost it as it evolved. There are known ways for a bar to fade or break apart. For instance, if the galaxy pulls in too much gas and redistributes its mass, or if a mild merger disrupts its inner orbits. But even then, traces usually linger. Ghostly spiral arms, loose dust lanes, or at least some spectral distortion. Deep observations of Hoag's object, however, reveal nothing. The core is unsettlingly pristine, as if mocking anyone hoping to find leftover scars. This cleanliness also ties directly to the mysterious outer ring. If the ring formed through a collision, we'd expect messy debris in the core, stretched streams of stars, leftover gas or dust. If it formed by slowly accreting gas, we might still see subtle inflows or asymmetries. But here, there's nothing. The golden core sits silent and dust-free, rotating lazily as if unaware of the vibrant young ring encircling it. Dynamically, the lack of a bar or spirals makes the ring even harder to explain. In many galaxy models, bars help move material onto stable orbits, setting the stage for rings to form. Spirals can also shepherd gas into specific regions, triggering star formation along a ring. Remove both, and you lose the usual tools that build such perfect outer structures. It's like finding a factory with no supply chain, yet somehow it keeps producing. New hypotheses have emerged to fill this gap. One idea is that Hoag's object isn't a typical disk galaxy at all, but an ancient elliptical that collected fresh material in an entirely different way. Without a disk or bar, incoming matter could have settled into a smooth, round ring shaped by a calm, dark matter halo. This scenario could explain the quiet core and lack of spiral features. But it raises a deeper puzzle. Why would this dark halo be so perfectly balanced, able to maintain such an ideal ring when most galaxies can't? Another bold proposal is that Hoag's object might be the product of a rare galaxy rejuvenation. In this picture, an old elliptical slowly and gently drew in an enormous reservoir of gas without disturbing itself. Instead of forming a turbulent, messy spiral disk, the gas stabilized into a thin circular ring and gradually birthed new stars. Because the process was so slow, the core stayed intact and never developed a bar. It's an elegant theory, but nearly impossible to confirm, since we've hardly ever caught another galaxy in the act of such quiet rebirth. The missing bar and spirals also challenge how we use Hoag's object to test our cosmic models. Most galaxy simulations assume disks and bars naturally emerge over long timescales. A galaxy with an actively star-forming ring but no such structures suggests our models might be incomplete. Perhaps there are calmer evolutionary pathways where galaxies stay strangely symmetrical without bars. Or maybe we're underestimating the power of dark matter in sculpting galactic shapes. Beyond the science, Hoag's object inspires an almost emotional response. Look at a typical spiral galaxy and you see movement, complexity, swirling arms, drifting dust, chaotic flows. Hoag's object, by contrast, feels abstract and deliberate, like a perfect geometric symbol adrift in a messy cosmos. It's the feeling of stumbling upon a flawless classical temple deep in the wilderness. Something so ordered, and still it feels almost unreal. Many astronomers admit that it's this absurd simplicity that haunts them. In the universe, simplicity is rarely natural. Chaos is the rule. Order must be explained. Yet here we have a galaxy almost flawless. No bar, no spirals, no dust. It shakes our confidence that current models can describe every kind of galaxy we might find. Perhaps the most fascinating thing about Hoag's object is this blend of simplicity and mystery. If it were cluttered with complex structures, we could fall back on familiar scenarios. But its clean, almost featureless form leaves every theory grasping for footing. It's like a perfectly polished mirror reflecting the gaps in our understanding. The longer you look, the more you feel how little you know. And maybe that's why Hoag's object captivates not just scientists, but anyone who loves the night sky. In a universe where most galaxies are tangled and unruly, it floats there. A quiet, perfect circle, a question without words. Why is it missing the structures we thought were universal? How can it remain so stable without the usual gears of galactic evolution? And most of all, is Hoag's object a true one-of-a-kind, or just the first of many silent, hidden galaxies waiting to be found? The answers remain out there. But it's almost perfect emptiness. The barless, spiral-free clarity of Hoag's object has turned it into a blank map, daring astronomers to redraw their understanding of how galaxies form and change. Every time we gaze at that immaculate ring, we're reminded that the universe can still astonish us, not with chaos, but with breathtaking, inexplicable simplicity. In the universe, perfect symmetry is almost a luxury. Most galaxies we know are beautiful in their own, imperfect way. Spiral arms can fall out of rhythm, cores stretch or warp slightly, disks tilt, and even the roundest galaxies hide subtle asymmetries if you look closely. The reason lies in the universe's restless nature. From the moment they formed, galaxies have been endlessly disturbed, tugged by the gravity of neighbors, grazed by smaller companions, swept by intergalactic gas flows. That's why something as perfectly circular as Hoag's object is so astonishingly rare. It's like finding a flawless droplet of water in the middle of a sandstorm, something that, statistically, should almost never happen. At first glance, you might think it's round. So what? But the blue ring of Hoag's object isn't just round to the naked eye. It's so perfectly round that even precise measurements show almost no deviation. The ring's width stays remarkably uniform for tens of thousands of light years. Its light is evenly spread along the entire circumference. No section glows brighter or fades into darkness. Ring galaxies created by collisions or resonance usually have at least a slight wobble, a lopsided stretch here, an uneven clump of stars there. Hoag's object is different. Its uniformity is so extreme that astronomers once used it to test image processing algorithms. If software introduced any distortion at all, this galaxy would expose it instantly. The mystery deepens when you consider where it lives. Most galactic asymmetry comes from outside interference, a nearby galaxy warping the disk, an ancient collision leaving scars, or simply uneven flows of intergalactic gas. But Hoag's object drifts in profound isolation. There are no large galaxies nearby to disturb it, no heavy streams of matter rushing in from cosmic structures. It's like an island floating on a perfectly calm sea. This solitude may help preserve its shape over billions of years. Yet even isolation isn't enough to explain such perfection. Truly solitary galaxies still wobble a little. Internal vibrations, uneven distributions of dark matter, or small historical ripples tend to leave marks. Hoag's object seems untouched by any of it. That has forced astronomers to rethink how galaxies hold themselves together. A ring of stars this wide and stable would need an extraordinarily balanced gravitational field. If the dark matter halo around Hoag's object is perfectly shaped, it could create the even pull needed to keep the ring circular over cosmic time. But most models predict that halos get slightly wrinkled by past interactions. Was Hoag's object truly untouched from the beginning, never colliding, never pulled hard enough to lose symmetry? Or does it possess a uniquely smooth halo, an exotic dark matter distribution we've never seen elsewhere? Some researchers go further, suggesting this perfect roundness might hint at new physics. If gravity doesn't work exactly as our standard models predict, or if dark matter behaves differently than we think, such an immaculate ring could be a clue. Supporters of MOND, modified Newtonian dynamics, have pointed to Hoag's object as an intriguing test case. If current laws can't reproduce its symmetry, perhaps we're missing a fundamental piece of how galaxies feel gravity. Beyond the equations, its symmetry stirs something deeply human, a sense of unnatural beauty in a chaotic cosmos. Most galaxies look like hand-drawn sketches, gorgeous but flawed, with uneven sweeps and broken curves. Hoag's object feels like a circle drawn with a compass, so exact it's almost suspicious. Many first-time viewers assume it's a digital render or an artist's creation. Even NASA admitted that when the Hubble image was released in 2002, the public struggled to believe it was real, a cosmic structure so clean it seemed artificial. That near-perfect geometry raises another question. Is it pure chance, or the result of some exquisitely gentle process? If the ring formed through slow gas accretion, perhaps billions of years of calm allowed it to smooth into shape. If it came from an extraordinarily delicate collision, maybe its matter was arranged just right. Mass, speed, and gravity all balancing with surgical precision. Yet both scenarios demand an almost unrealistic level of finesse, a process so quiet it left no chaos behind, and long enough for everything to settle into flawless symmetry. Computer simulations struggle here. Collision-based rings tend to warp, grow uneven, or drift out of shape over time. Gas-formed rings often end up slightly lopsided because no inflow is truly uniform. To make one like Hoag's object, researchers must fine-tune their models to almost absurd degrees, assuming a perfect halo, an impossibly gentle past, and an evenly fed gas stream as if programmed by hand. That has led some to suspect we're missing deeper rules about how such structures form. Ironically, this perfection makes the galaxy harder to study. Asymmetrical galaxies leave scars, tidal tails, twisted arms, dust trails, breadcrumbs that let scientists reconstruct their past. Hoag's object leaves almost nothing. It's like a room meticulously cleaned of every clue, leaving cosmic detectives with nowhere to start. All we have is a perfect circle and silence. Yet that silence turns it into a unique natural laboratory. Astronomers have used its flawless ring to probe galactic dynamics with extraordinary precision. Because it's so uniform, even the slightest irregularity in rotation speed or mass distribution shows up clearly in its light spectrum. That makes Hoag's object an unusually sensitive test for dark matter models and theories of gravity. Each new measurement of its stellar motions asks our physics a simple question: can you explain perfection? But beyond science, Hoag's object speaks to the imagination. It evokes the ancient symbol of the circle: wholeness, infinity, order rising from chaos. In a universe of broken, misshapen galaxies, it appears like a pure sign, as if some invisible hand drew it to challenge our understanding. Perhaps that's why the Hubble photo in 2002 didn't just captivate scientists. It spread widely among the public, shared not for data, but for its almost unbelievable beauty. Its improbable symmetry reminds us of something science sometimes forgets. The universe isn't just data, it's art. Equations and models can try to replicate that ring, but the awe it inspires can't be calculated. It's proof that amid chaos, order can emerge, sometimes defying every probability. And that, more than anything, is why Hoag's object isn't just an odd galaxy. It's a symbol, a quiet reminder that the cosmos can still outwit our imagination. If the perfect symmetry of Hoag's object is a puzzle for geometry, the way it spins is a headache for physics. A galaxy isn't just a static picture, it's a colossal machine in motion. And when astronomers measured the rotation speeds of the stars in Hoag's object's luminous blue ring, they found something that didn't fit any familiar formula. Its rotation curve, the plot showing how stellar velocity changes with distance from the galactic center, refuses to follow the standard dark matter halo model we usually rely on to explain the motion of most galaxies. This is where Hoag's object touches one of modern cosmology's deepest questions: how dark matter is really distributed and whether our understanding of gravity is correct. To see why, we need to go back to the 1970s, when scientists discovered a striking paradox. Galaxies spin much faster than their visible mass can explain. If you count only the stars, gas, and dust, their gravity isn't strong enough to keep the outer stars from flying away. And yet, those stars stay put, moving steadily around the galactic core. This led to the idea of dark matter, an invisible, non-luminous substance making up most of a galaxy's mass, holding it together through gravity. In the standard picture, every galaxy sits inside a vast dark matter halo, spreading far beyond its visible disk, keeping everything bound. For most observed galaxies, this halo model works well. Rotation curves usually flatten in the outer regions, meaning stars far from the center orbit almost as fast as those closer in. But when astronomers analyzed the data for Hoag's object, something strange appeared. Its rotation curve isn't as flat as expected. There are subtle dips or slower rises where the smooth dark matter halo model predicts a steadier speed. Some studies suggest that Hoag's object seems to have less dark matter than usual, or that its dark matter is distributed in an odd, non-typical way. That's puzzling, because maintaining such a wide, young, and perfectly circular ring for billions of years requires a very stable gravitational pull, something the standard dark matter halo usually provides. Here, the halo seems either too weak or shaped differently. One idea is that Hoag's object has a much more compact, smoother dark matter halo than expected. Instead of stretching far out, the halo might be concentrated closer to the core, so gravity drops off faster at large distances. That could explain the unusual rotation curve. But if the halo is too concentrated, the outer blue ring shouldn't stay perfectly stable. It would be harder to keep those stars on neat circular paths for so long. Yet the ring looks flawless, which makes this scenario unconvincing. Another possibility is that the halo isn't smooth at all, but layered or hollow in places. Such a structure could create a gravitational field that changes with radius, producing unpredictable rotation speeds. But then another question arises. How could such an irregular halo keep a ring so perfectly balanced? Normally, if gravity isn't even, a stellar ring would warp, clump, or thicken unevenly. The combination of a mathematically perfect ring and a non-standard rotation curve feels like a paradox. This tension has led some astrophysicists to bring up MOND, modified Newtonian dynamics. MOND proposes that at extremely low accelerations, such as in the outskirts of galaxies, Newton's law of gravity, and even Einstein's, might behave differently. MOND has explained the rotation curves of some galaxies without requiring massive dark matter halos. Hoag's object seems like an ideal test case. A very distant, very even ring, plus a rotation curve that defies the standard halo model. If MOND is right, it should explain how the ring stays so stable without a huge invisible mass holding it together. But MOND struggles with Hoag's object's almost perfect symmetry. Its equations predict smooth changes in gravity, but have trouble producing such an exquisitely stable orbit without tiny long-term wobbles. MOND also tends to break down at larger cosmic scales, like galaxy clusters and gravitational lensing. So while Hoag's object invites people to consider MOND, it's far from proof that dark matter is wrong. Other scientists think maybe the real issue isn't the halo or gravity itself, but how we understand ring formation. Perhaps this ring was built through an unusually calm, slow gas accretion process in an extremely quiet environment. So its stars move in ways our standard, more chaotic galaxy models don't predict. But that's more like adding an exception to save the theory than providing a clean, general explanation for why Hoag's object is so different. It's worth noting that our rotation data for Hoag's object isn't perfect. The galaxy sits about 600 million light-years away, so measuring the motion of individual stars in the ring is impossible. Astronomers have to rely on the combined light spectrum, studying the Doppler shift of hydrogen gas and young stars. That can miss fine details or introduce modeling errors. Researchers hope that future observatories, like the Square Kilometre Array or the Extremely Large Telescope, will deliver sharper data, letting us truly test both dark matter halo models and MOND against Hoag's object. Despite the debate, one thing is clear. Hoag's object is a rare but powerful test for any theory of dark matter and gravity. Because it's so round and so clean, even tiny differences in mass distribution show up in its rotation curve. In other words, it's an almost perfect natural laboratory. No central bar to stir things up, no messy spiral arms, no dust clouds, no chaos. A galaxy this pristine is the perfect place to challenge our hidden universe models. The mystery of Hoag's halo also hints at something bigger. Maybe not all galaxies follow the same dark matter recipe. We often assume every galaxy sits inside a similar halo, just scaled in size and density. But what if there are exceptions? Halos that are weak, odd, or formed in unusual ways? That would open a new chapter in understanding how the cosmos evolves. Hoag's object might be a clue that dark matter isn't as uniform as we think, or at least that its relationship with ordinary matter is more complicated than our neat models suggest. Beyond the science, Hoag's dark matter puzzle carries a quiet philosophical weight. It reminds us that what we see, the glowing blue ring, the calm golden core, is just the tip of a cosmic iceberg. The real engine of this galaxy's existence is invisible. We're staring at near perfection, yet most of its mass, if it's there at all, can't be seen. And we're not even sure it exists in the way we imagine. Looking at Hoag's object is a humbling experience. After half a century of dark matter studies and thousands of halo models, one strange galaxy can still shake our confidence. It's like a tough final exam, forcing our theories to prove themselves against something too clean and too unique to dismiss. Perhaps one day, Hoag's object will help us refine our understanding of halos, or even spark a revolution in how we think about gravity. And whatever the ultimate answer turns out to be, a strange halo, MOND, or something entirely new, the dark matter mystery of Hoag's object is a powerful reminder. The universe is far vaster and subtler than we imagine. Within that perfect circle, where young blue stars blaze around an ancient golden heart, hide forces we still can't name. It's this contrast between a simple, elegant shape and physics deep enough to overwhelm us that has kept Hoag's object fascinating and confounding astronomers for more than 70 years. One of the most puzzling and thrilling discoveries about Hoag's object has nothing to do with its perfectly round shape. It's about what surrounds it, a gigantic halo of neutral hydrogen gas. In the cosmos, hydrogen is the most important raw material for making stars. Whenever you spot a region bursting with young stars, there's almost always a supply of cold hydrogen drifting in, feeding the stellar nursery. But in Hoag's object, even though the outer ring is blazing with newborn stars, observations reveal something strange. The hydrogen is there, plenty of it, wrapping the galaxy like a colossal blanket. But it seems still. No clear streams, no sign of gas falling inward to fuel star formation. It's as if the brilliant blue ring is sustaining itself without any help, a scenario that breaks the usual playbook of galactic evolution. To grasp why this is so odd, we need to revisit how galaxies rejuvenate and make stars. Star formation is hungry work. It burns through vast amounts of gas. Young stars quickly devour the fuel around them, and without fresh supply, star birth slows dramatically in just a few 100 million years. Yet spectra of Hoag's object show its blue ring has been forming stars steadily for at least that long, maybe longer. If no new gas is coming in, that process should have petered out ages ago. But it hasn't, which leads to the big question. where is the fuel coming from? Astronomers searched for answers by mapping the hydrogen around the galaxy. They found an enormous reservoir surrounding the ring. But to their surprise, the gas is almost motionless. It shows no chaotic flows, no streams rushing inward. Doppler velocity measurements reveal most of the hydrogen is in equilibrium, simply rotating with the galaxy rather than raining down as fuel. That's unlike other vigorous star-forming galaxies, where hydrogen is usually caught streaming into the disk or ring at measurable speeds. Some researchers have suggested the gas might have flowed in long ago, leaving behind a leftover reserve, now being slowly depleted. If that's true, the blue ring could be burning through its final stash of fuel and will eventually fade, in cosmic terms, maybe within a few 100 million years. But this idea runs into a problem. To sustain star formation for so long, the gas would have needed to be far denser than what we see today. Current data show it's relatively diffuse, not the rich reservoir such a long-lasting starburst would require. Another possibility is that gas is indeed flowing inward, but so slowly and smoothly that we can't detect it. If the inflow is extremely gentle and uniform, it might leave no strong velocity signals for our instruments to pick up. In that case, the ring could be fed by a hidden stream, too subtle to see with today's tools. But this raises another issue. To keep star formation running in such a perfectly balanced structure, that stream would have to be astonishingly fine-tuned, not too strong to stir chaos, not too weak to let the ring starve. Such precision is hard to imagine for a natural process. A bolder idea is that the surrounding hydrogen could be ultra-cold and hard to detect, or in a form our instruments aren't sensitive enough to spot. Some models suggest very cold gas might not emit the usual radio signals we use to map hydrogen, meaning we could be missing most of the real fuel. If so, Hoag's object might be quietly feeding on an invisible hydrogen ocean. But so far, there's no direct evidence for such a hidden mass of gas. The hydrogen's eerie stillness has also led scientists to question the galaxy's past. Perhaps Hoag's object once went through a violent energetic event, maybe an outburst from a supermassive black hole that swept its inner regions clean, carving the vast empty gap between the core and the ring. Afterward, only the distant hydrogen survived, now passively surrounding the galaxy. The blue ring could then be a remnant of a short-lived rebirth, forming from leftover gas that will eventually run out. The snag is that the galaxy's core shows no clear signs of having hosted such a dramatic black hole outburst, at least not at the scale we usually see in galaxies with similar scars. Some have even wondered whether dark matter might be keeping the gas so calm. If Hoag's object's dark halo is unusually smooth and symmetric, it could hold hydrogen in a stable state, not letting it collapse inward, but not letting it drift away either. But this clashes with other evidence. The galaxy's rotation curve doesn't behave like a neatly smooth halo. Once again, the dark matter story and the hydrogen story seem entangled, but not quite fitting together. This mystery of fuel supply has bigger implications for astronomy. If a galaxy can keep making stars without obvious gas inflow, maybe our models of the galactic fuel cycle aren't complete. We usually think galaxies either pull in fresh gas from the intergalactic medium or rely on huge internal reserves to keep star formation going. Hoag's object seems to do neither, or at least does it in a way we don't yet understand. That forces researchers to rethink how gas moves, accumulates, and sustains life in isolated galaxies. Beyond the science, the image of a young stellar ring fed by a silent sea of gas carries a haunting symbolism. It's a picture of quiet resilience, creation happening even when everything seems still, powered by hidden forces we have yet to uncover. The glowing blue ring is like a meadow blooming in the middle of a desert, while the calm hydrogen halo feels like an unseen atmosphere, both nurturing and defying our understanding. Future ultra-sensitive radio telescopes, such as the Square Kilometer Array, along with next-generation millimeter-wave observatories, will be crucial in solving this puzzle. They might detect faint, cold gas streams or subtle signals we currently miss. If they find evidence of a hidden flow, we'll gain vital clues about how galaxies like Hoag's object sustain star formation in isolation. If they don't, we may need to rewrite our theories of how galaxies feed themselves and evolve. Whatever the answer turns out to be, the quiet hydrogen halo of Hoag's object remains a captivating paradox. It reminds us that even when we think we understand how galaxies eat, breathe, and build stars, nature still hides exceptions that defy our frameworks. And it whispers that beneath Hoag's object's calm, symmetrical face lies a far more intricate story. A young stellar ring, living off an invisible fuel supply, adrift in a silent ocean of hydrogen we can't yet decode. That very stillness, more than the ring's bright glow, is what makes Hoag's object one of the most fascinating natural laboratories the universe has offered to science. When astronomers examined the light from Hoag's object through a spectroscope to decode its chemical makeup, they didn't just collect a dry list of elements, they stumbled upon a hidden story, a chemical diary quietly written by the galaxy itself. And that story only deepened the mystery. Instead of revealing the messy, chaotic past typical of galaxies, Hoag's object carried a chemical signature so uniform, so unnervingly calm, it almost felt unreal. It hinted that the galaxy's striking young blue ring came from outside material, yet that material must have arrived with an almost impossible gentleness, a rarity in a universe ruled by collisions and violence. To understand why this is so shocking, we need a bit of chemical astronomy. Stars don't just shine, they're the universe's forges. As they age and die, they create elements heavier than hydrogen and helium, what astronomers broadly call metals. Each new generation of stars forms from gas that has been enriched or recycled by older stars, making it more metal-rich over time. So a star's metal content is a powerful clue about the history of the gas it was born from. A galaxy that's been forming stars for eons will have metal-rich gas, while pristine gas from intergalactic space or small, undeveloped galaxies tends to be poor in metals. When scientists analyzed Hoag's object, one thing stood out clearly. Its golden central core is metal-rich, exactly what you'd expect from an old, well-lived galaxy. But the young stars in its dazzling blue ring are far more metal-poor. This means the ring's material didn't come from the core. If gas had been expelled outward, it would share the same enriched composition. Instead, the blue ring seems to have formed from some external, more primitive gas that had barely been processed by previous generations of stars. Perhaps it came from the intergalactic medium, or a small, gas-rich but underdeveloped galaxy. It's strong evidence that the ring isn't just an extension of the core, but a completely new chapter in the galaxy's life, fueled by foreign material. Yet the most startling discovery is how chemically uniform the ring itself is. In most galaxies, even if external gas is involved, it rarely mixes perfectly right away. You'd expect to see patches with different metal levels, places where native and pristine gas swirl together imperfectly, or where star formation hasn't fully homogenized the chemistry. But in Hoag's object, the young stars across the entire ring share nearly the same metallicity. No matter where you look on that vast cosmic halo, the chemistry is strikingly even. This suggests the ring's gas was blended with extraordinary thoroughness before stars began to form, and the mixing must have happened quietly, without the usual signs of dynamical upheaval. That's bizarre compared to the usual galactic playbook. In a collision, gas is ripped apart, whipped into turbulent streams, and left chemically patchy. Even gentler mergers rarely reach perfect uniformity. By contrast, creating a ring of young stars as even as Hoag's objects would require a slow, delicate stirring process. Gas settling into the galaxy's halo, calmly mixing over a long time before collapsing to form stars, with no major shocks or violent disruptions. Some researchers have proposed a slow, cold gas accretion scenario. If Hoag's object has been sipping hydrogen from intergalactic space over billions of years, that inflow could have had time to spread out and homogenize before becoming dense enough to trigger star formation. Such a quiet buildup wouldn't jolt the galaxy's structure, allowing metals to dilute evenly. But this idea demands extreme cosmic patience. Billions of years of gas marinating before the first new stars appear. And so far, astronomers haven't caught another galaxy in the act to confirm this process. Another possibility is that Hoag's object once swallowed a primitive gas-rich dwarf galaxy, one that had formed few stars and remained metal-poor. If the merger were astonishingly gentle, its gas might have dispersed and mixed evenly into Hoag's halo before igniting star formation. But that would require an almost unrealistic level of calm. The dwarf would need to dissolve seamlessly, leaving no visible debris or tidal tails. Deep observations around Hoag's object so far haven't found such leftovers. Some have speculated that the galaxy's dark matter halo could act as a giant mixer. If Hoag's halo is unusually smooth and symmetric, it might help blend infalling gas without triggering strong turbulence. But this is only a hypothesis, and it runs into its own problems. Notably, Hoag's object's odd rotation curve, which doesn't match the clean, idealized halo this idea would require. These chemical riddles aren't just trivia about elements, they're key clues to the galaxy's formation history. The evidence almost rules out familiar scenarios. Hoag's object is likely not a simple aging disk galaxy reborn from its own gas, nor the result of a dramatic collision. Instead, it seems to be a galaxy that slept quietly for eons, slowly gathering or siphoning gas from its surroundings in some remarkably gentle way, enough to mix everything thoroughly before awakening into its current burst of star formation. That quiet rebirth carries a strangely philosophical weight. In a universe where violence usually drives growth, galaxies collide, black holes erupt, shock waves tear through gas. Finding one that seems to have come back to life in silence feels improbable. It's like discovering a lush garden thriving in a desert with no trace of storms. Hoag's object isn't just an oddity of shape, it's an oddity of history, proving that galaxies might renew themselves without chaos. For astronomers, this idea is profound. If Hoag's object isn't unique, the cosmos may hide many other galaxies that quietly rekindled their star-making engines without leaving obvious scars. That would push us to rethink galaxy evolution, expanding the narrative beyond a tale dominated by collisions and violence, toward a richer picture that also includes subtle, graceful renewal. In the end, when we look at Hoag's object's perfectly even blue ring, we're seeing more than a stunning circle of young stars. We're reading a chemical record of an extraordinarily peaceful past, perhaps billions of years of quiet gas gathering and mixing before new life finally ignited. In a universe known for noise and impact, Hoag's object is like a slow, quiet symphony, a story of rebirth without explosions, challenging our oldest assumptions about how galaxies grow and change. In galactic astronomy, rotation is often the biggest storyteller. It's the heartbeat of a stellar metropolis, revealing its past, its inner structure, and even its present health. When astronomers began measuring the spin of Hoag's object, they expected a smooth transition from the core to the outer ring, the way most galaxies behave. The center turns a bit slower, the speed rises or levels off farther out, and somewhere in between, there's usually a messy transition zone where orbits get scrambled to fit the galaxy's overall shape. But Hoag's object refuses to follow that script. Its ancient golden core turns lazily, almost indifferent to the universe around it, while the youthful blue ring spins fast and steadily, as if it's an entirely separate system. There's no turbulent middle ground, no sign of orbits colliding or blending. Two worlds exist side by side, yet they seem not to speak to each other. To feel how strange this is, first picture a typical disk galaxy. Its core usually rotates slowly, not motionless, but dragged along by the immense mass of the galaxy and the pull of its dark matter halo. Moving outward, stellar orbits tend to settle into a plane, forming a disk or a ring, but the process is rarely seamless. There's almost always a transition zone, where stars and gas stretch, twist, and swirl chaotically before settling into the main flow. That chaos is the fossil record of galactic history. Mergers, collisions, or streams of gas pouring in from intergalactic space. It's like the messy interchange between a city's streets and a highway. Hoag's object has no messy interchange. Orbital speed measurements, made by tracking the Doppler shift of starlight and hydrogen gas, show that its elliptical core spins slowly, almost idly, while just beyond the vast empty gap, the blue ring whirls with perfect balance, fast and calm like a polished disc. Between them lies a near-perfect void, not just of matter, but of motion itself. There's no sign of stars being tugged back and forth or having their orbits disturbed. It's as if someone placed a spinning record around a still globe, and the two have coexisted untouched for billions of years. This asynchronous rotation puzzles astronomers. How can two galactic components form inside one galaxy and yet not be dynamically connected? If the blue ring were born from the golden core, you'd expect at least some overlap, some chaos where gas and stars were flung outward to build the ring. On the other hand, if the ring came from outside, it should have gone through a turbulent settling phase. But Hoag's object shows no trace of such a noisy past. One idea suggests the ring formed from an external stream of gas that the galaxy's dark matter halo caught and locked into a stable orbit, never touching the core. That would let both parts evolve separately. The old elliptical center kept its slow spin, while the ring established its own fast, clean rotation. But this would require an almost perfect balance, a halo strong enough to hold the ring in place, yet smooth enough not to disturb or warp it over time. That's a rare, almost ideal setup in a universe where most galaxies bear the scars of collisions. Another scenario imagines the blue ring as the remains of a smaller galaxy captured and gently absorbed by Hoag's object. If that smaller galaxy had a perfectly circular slow orbit, it might have unraveled into a rotating ring without merging into the core. But such a delicate capture would demand an extraordinarily precise speed and approach angle. Even a slight misalignment would have led to a crash or a warped orbit. And once again, Hoag's object shows no leftover debris that such a capture should have left behind. Some scientists think the vast gap between the core and the ring might be a dynamical buffer zone, a region where the combined gravity of the halo and the core makes orbits unstable, preventing matter from lingering there. If true, this could explain the emptiness and the clean separation. But no one has yet shown exactly how such a perfect buffer could form, and current computer models struggle to reproduce it. What makes Hoag's object's split rotation so important is how directly it challenges our core ideas about galactic evolution. Most models assume galaxies eventually settle into a single balanced rotation. Any new material will, over time, join the common spin. Hoag's object proves there's at least one exception: a galaxy that can host two completely independent rotating systems for billions of years and still remain stable. If that's possible, we may have underestimated how diverse galactic dynamics can be. For observers, this separation is a scientific gift. Because the core and ring don't mix, astronomers can study each almost in isolation. The old golden heart preserves clues to the galaxy's ancient beginnings, while the blue ring acts as a pristine lab to test how fresh material can organize into a flawless disk without turbulence. The empty gap makes measurements cleaner, free from the interference of stray gas or dust. On a deeper level, this asynchronous dance is hauntingly poetic. Hoag's object feels like a two-part symphony, a slow, somber melody at its aging center, and an energetic, youthful rhythm circling outside. Between them lies a silent gulf, an invisible boundary that neither has crossed. It's a striking visual and conceptual contrast, a reminder that the cosmos doesn't always follow simple, uniform rules. In the broader context of science, this dual rotation is pushing theorists to rethink the basics. Maybe dark matter doesn't just hold galaxies together, but can carve out stable, separate zones, letting multiple systems spin under one roof. Or maybe our laws of gravity still miss subtle effects in low-acceleration, low-density regions. Every new velocity map of Hoag's object tests these ideas, and could one day force a rewrite of how we understand galactic motion. But even before those mysteries are solved, Hoag's object has already given us something beautiful: the story of a galaxy that keeps two hearts beating to different rhythms, side by side, for eons. It shows that even in a universe ruled by gravity, a force that tries to mix everything together, there's room for individuality. Its quiet core and lively ring, each living on its own time and speed, prove the cosmos is more intricate, delicate, and surprising than our neat models often assume. And maybe that's the true magic of Hoag's object: a galaxy that's breathtaking, not just in form, but in the sheer audacity of its independence. Two perfectly tuned hearts spinning apart, yet together, for billions of years. Hoag's object isn't just strange because of its shape, its makeup, or the way it spins. It's strange because of where it lives, an almost forgotten spot in the vast emptiness of the universe. When astronomers mapped the space around this galaxy, they found it doesn't belong to any dense cluster. It's not sitting on one of the busy cosmic highways where galaxies constantly interact, and it has no nearby giants tugging at it with their gravity. It's like a lone island in a boundless ocean, far from any shore. That solitude may be the very reason it has stayed so eerily perfect, but it also makes its origin story far more puzzling. To see why isolation matters, imagine galaxies in crowded clusters. There, gravity from dozens or even hundreds of neighbors constantly pulls and twists, warping star disks, breaking symmetry, and often causing spectacular collisions. Galaxies in such environments rarely keep their shapes for long. Hoag's object, on the other hand, seems to have lived unbothered for billions of years. No massive neighbors to distort its orbit, no streams of matter crashing in to upset its balance. This quiet may have allowed its delicate blue ring to stay stable, unwarped, undisturbed by outside forces. That peace also explains why Hoag's object can be nearly perfectly symmetrical. In space, even a gentle gravitational nudge from a nearby galaxy can distort a circle. A minor collision, or even a distant gravitational flyby, can stretch or bend orbits and leave scars in the structure. But Hoag's object appears to have avoided all of that. It floats in a sparse region with no one close enough to interfere. Once its ring formed, it's been able to spin in perfect balance for billions of years. But this calm raises a big paradox. If Hoag's object is so alone, where did it get the fresh material to build that bright, youthful blue ring? In crowded cosmic neighborhoods, galaxies often feed on new matter, swallowing dwarf galaxies, siphoning gas from intergalactic streams, or exchanging material during collisions. Hoag's object has no such suppliers. It sits in a galactic desert with no obvious reservoirs of fresh gas. If it has no neighbors to devour and no strong gas streams to tap, how did it rejuvenate itself into the vibrant ring we see today? One idea is that this isolation wasn't always so extreme. Billions of years ago, Hoag's object might have passed near a gas cloud or a small companion galaxy. It could have slowly consumed that material, then drifted away, leaving it alone in today's void. The process might have been so slow and gentle that no trace remains for us to detect now. In this picture, Hoag's object is like a cosmic nomad that once stumbled upon a gas oasis, drank it dry, and now wanders alone in the desert. The trouble is, modern telescopes, sensitive enough to spot faint remnants in similar cases, haven't found any leftover streams or dwarf galaxies to support this idea. Another possibility involves the cosmic web, the vast network of gas filaments and dark matter connecting galaxies. Even in a sparse area, Hoag's object might still be linked to a thin, invisible thread of this web. If it has been quietly pulling in gas from such a filament over billions of years, it could have built up enough fuel to create its blue ring without ever colliding with another galaxy. This would be a slow, gentle process, perfectly in line with the serenity we see. But detecting such faint gas streams across such distances is extremely difficult, and current observations aren't sensitive enough to confirm whether this silent supply line really exists. Some scientists also wonder if Hoag's object's dark matter halo might act as a kind of gas trap. A halo could pull in and hold on to gas from the wider environment, slowly building a calm reservoir around the galaxy. Over time, the gas could cool and collapse into the ring of stars we see, without any violent inflows. This fits with the detection of a quiet hydrogen halo. But it raises another question. Why can this halo do what most others can't? Could its shape be unusually smooth, or does its evolutionary history set it apart? Isolation also shapes the lifetime of the ring itself. Without nearby galaxies to disturb it, the ring can remain stable for extraordinary lengths of time. This is why scientists believe Hoag's object's blue ring has lasted hundreds of millions, perhaps billions, of years without breaking apart. In denser regions, rings are usually warped or disrupted much sooner by gravitational encounters. Hoag's object is like a natural laboratory where we can study the slow, undisturbed evolution of a nearly perfect structure. But this very solitude makes decoding its past frustratingly hard. In galaxies that have interacted, astronomers can trace history through tidal tails, star streams, messy gas clouds, and other debris. Hoag's object has none of that. It's like a room scrubbed clean of all clues, leaving only a flawless design. No neighbors means no comparison points, no collision scars to date, no obvious gas flows to follow back in time. That's why Hoag's object holds such a unique place in astronomy. It's both an ideal specimen for studying long-term stability and a maddening puzzle because its history is almost invisible. It challenges our galaxy formation models, which often rely on interaction and environment. And it forces us to consider that there may be more hidden galaxies like this, quiet outliers evolving on their own, far from the busy hubs of cosmic activity. On a more emotional note, there's a haunting beauty in Hoag's object's loneliness. Picture a perfectly round galaxy, spinning silently in a nearly empty stretch of space, untouched, unbothered, keeping its rare symmetry for billions of years. It's like a forgotten work of art in the Museum of the Cosmos, unscathed by time, safe from the chaotic currents that tear through galaxy clusters. Its solitude turns it into a mirror for our own curiosity. In a universe where chaos and collisions are the norm, could there still be galaxies hiding in peace, quietly carving out their own order? Future studies of Hoag's object's surroundings could be key. Next-generation radio and X-ray telescopes may detect faint gas flows or ultra-dim dwarf galaxies if they're there. If we find signs of an ancient supply of fuel, we might finally understand how an isolated galaxy can refresh itself. If we don't, we may have to accept that Hoag's object has sustained itself in an entirely new way, one science has never seen before. Either way, its isolation is central to its allure. That silent environment has kept it pristine, a perfect circle adrift in space. A reminder that even in a turbulent universe, there can be places so still and remote that order and balance endure for billions of years. Yet that same solitude is also why it remains unsolved. No collision history, no clear gas streams, no neighborly clues. Just a breathtakingly improbable galaxy, quietly turning in the deep cosmic dark. When the Hubble Space Telescope first turned its gaze toward Hoag's object in 2002, the goal was simple: take a crisp image that could finally settle long-standing debates about the galaxy's bizarre shape. But sometimes the universe loves to play tricks, the kind that make astronomers laugh in disbelief. While Hubble was photographing the scene, it accidentally captured a detail that would become legendary. Right in the vast, eerie emptiness at the center of Hoag's object's glowing ring, far in the background, sat a second, smaller ring galaxy. Astronomers quickly nicknamed it Hoag's twin, a strange little sibling showing up exactly where no one expected it. At first glance, the Hubble image stuns because of Hoag's object itself: a shimmering blue outer ring, a smooth golden core, and a dark, almost surreal gap in between. But when scientists looked closer, they spotted a tiny and perfectly round light tucked in the center, hundreds of millions of light years farther away. It wasn't a stray star that happened to photobomb the shot. It was another ring galaxy, nearly the same rare shape as Hoag's object, only much smaller. It's like peering through a giant cosmic ring and by pure chance seeing another ring floating in perfect alignment behind it. The odds of two rare ring galaxies lining up so neatly are almost unimaginable. The discovery instantly caught both scientific and public imagination. Headlines called it a cosmic prank, a picture that tells a story, even the universe playing puzzle games. Look at the image, and it feels less like an accidental snapshot and more like a piece of art, deliberately arranged to spark wonder. One flawless ring galaxy is rare enough. To have a miniature copy centered inside it seems like someone intentionally placed it there to add mystery. Yet for astronomers, Hoag's twin isn't just a visual curiosity, it's an unexpected scientific gift. That distant little galaxy acts like a natural flashlight, its light passing straight through Hoag's object. By studying how that light is filtered and absorbed, scientists can probe the gases and dust surrounding Hoag's object, uncovering their chemical makeup and density, something that's normally very hard to measure. It's a bit like shining a beam through fog to see what it's made of. Hoag's twin lets us examine an otherwise quiet, elusive space in exquisite detail. Even more intriguingly, having a bright, compact, perfectly aligned light source makes it possible to measure Hoag's object's hydrogen halo and even its dark matter halo with unusual precision. As the twin's light travels through, it gets subtly absorbed and bent depending on the gas density and the hidden mass distribution. Astronomers can use these effects to test models of Hoag's object's unseen structure. That's especially exciting because this galaxy's dark matter has long been puzzling. Its rotation curve doesn't quite match standard predictions. In that sense, Hoag's twin is like an unexpected cosmic gift, offering a direct way to check competing theories. The strange alignment also challenges ideas about how galaxies are distributed across the universe. Ring galaxies themselves are rare. The chance of spotting two aligned so perfectly is even rarer. Some astronomers have run rough estimates suggesting the odds might be 1 in 10 million or smaller. That doesn't mean some invisible hand arranged it, but it reminds us that in a universe this vast, even events with vanishingly small probabilities will eventually happen. And sometimes, we're lucky enough to be looking at the right moment. Curious minds have asked, could Hoag's twin somehow be physically connected to Hoag's object? Maybe it once interacted and helped form the ring? The answer is almost certainly no. Distance measurements show the twin is far, far behind Hoag's object. Its light only happens to pass through the ring's heart on its way to us. They don't share an environment and have no chance of influencing one another. Strangely, that makes the scene even more poetic. Two ring galaxies, completely unrelated, yet from our vantage point, they form a flawless picture. In the public eye, the Hubble photo of Hoag's object with its twin spread widely through science and art communities alike. It became an iconic example of the universe's accidental beauty, the kind that makes even non-astronomers stop and marvel. Some researchers admit that this single image helped turn Hoag's object into a celebrity, sparking renewed interest and deeper studies. The unexpected sibling didn't just add scientific value. It transformed an already special galaxy into a cosmic symbol of elegance and wonder. Looking ahead, having a background galaxy shining exactly through the center has huge potential. New observatories from the James Webb Space Telescope to next-generation radio arrays can use Hoag's twin to study the cold gas, dust, and dark matter around Hoag's object with unprecedented sensitivity. Every photon traveling through that space carries precious information, and having a lucky built-in light source saves astronomers the trouble of searching for one. On a more poetic note, the site invites reflection. In the middle of a perfect lonely ring galaxy, there's a tiny sibling far away, a silent reminder that the universe, even in its vast solitude, can weave surprising connections. These galaxies will never meet, yet the twin's light still passes through, as if offering a fleeting glance to a stranger. It makes Hoag's object feel a little less alone in our imagination, even if physically it truly is an isolated island. Ultimately, the discovery of Hoag's twin in that 2002 Hubble image underscores a profound truth. The universe isn't only a place of strict laws and cold equations. It's also a stage for breathtaking coincidences. A perfect ring galaxy was already a mystery. Add a smaller twin perfectly centered behind it, and a routine scientific photo becomes both poetic and profound. This kind of randomness, the kind no simulation or prediction could foresee, is what makes exploring the cosmos so thrilling. There's always a chance we'll stumble upon something astonishing the moment we lift our eyes to the stars. When the Hubble Space Telescope turned its gaze toward Hoag's object in 2002, no one expected a revolution. Astronomers were simply hoping for a sharper image, something to confirm a long-standing hunch that this was a rare kind of ring galaxy, perhaps born from a process we still didn't fully understand. But when the final image appeared on the control room screens, everyone fell silent. Hoag's object didn't look like a galaxy scarred by the universe's chaotic past. It was too beautiful, too perfect, and most unsettling of all, too clean to fit any familiar story. It was like opening an old box, and instead of finding the mess you expected, discovering an object so exquisite it almost felt impossible. The Hubble photo revealed a completely new Hoag's object compared to the blurry images that came before. Its outer ring of young, blue stars was crisp and flawlessly round, as if drawn with a compass. Cool blue light spilled evenly along the circle, with no dim patches, no signs of twisting or breaking. The golden core in the center faded smoothly outward, untouched by dust lanes or scars of disturbance. Between the two was a pitch-black gap, sharp, empty, immaculate. No stray stars, no faint gas, no ghostly debris from ancient collisions. The whole structure looked unnaturally pure, almost otherworldly. For many astronomers, the moment was a shock. For decades, scientists had tried to piece together a reasonable history for Hoag's object. Maybe it once collided with another galaxy, throwing off a ring of stars. Maybe it used to have a bar and spiral arms that somehow disappeared. Maybe the ring formed from gas drawn in long ago. but every explanation seemed messier than what Hubble showed. There were no tidal tails, no shredded streams of stars, none of the usual scars left after a galactic upheaval. Hoag's object looked untouched, the exact opposite of how we think galaxies evolve. Suddenly, long-standing theories began to wobble. The collision scenario, the go-to explanation for most ring galaxies, didn't hold up. A crash violent enough to create such a massive ring should leave behind faint tidal debris, twisted gas, or at least some sign of disruption. Yet Hubble's view showed a smooth halo and a gap so pristine it felt deliberate. Resonance theories, where a bar or spiral waves create rings, also faltered, since there's no bar, no spiral disk inside the core to drive that process. Ideas about slow mergers or cold gas accretion hit similar walls. If they'd happened, there should still be leftover gas or stars mixing in. But there was nothing, just near-perfect symmetry. For the scientific community, it was thrilling and maddening all at once. On one hand, an object this breathtaking and this defiant of theory meant there were new mysteries waiting to be solved. On the other, the lack of any clues made it nearly impossible to trace its past. Hoag's object felt like a crime scene, scrubbed spotless. No witnesses, no fingerprints, just a flawless, enigmatic masterpiece. You know it must have a story, but every trace of it is gone, or maybe never existed. Outside the scientific world, the Hubble photo became an instant sensation. It spread across astronomy magazines, science blogs, and early social media. The public was captivated by its beauty, a glowing blue ring embracing a golden heart, so balanced it seemed designed by some higher intelligence. People compared it to abstract art, to minimalist logos. Some called it the Eye of the Universe. Others nicknamed it the Galaxies' wedding ring. Looking at it wasn't just a scientific curiosity. It stirred awe and a quiet recognition of beauty beyond imagination. That wave of fascination had an unexpected side effect. It sparked a new surge of research into ring galaxies and cosmic symmetry. Before Hubble, ring galaxies were a small, overlooked category, usually dismissed as odd leftovers of galactic collisions. But after 2002, Hoag's object became the benchmark, the test case for theory. Its near-perfect shape was used to challenge computer simulations and image processing tools. Dynamical models and dark matter distributions were tested against it to see if they could reproduce its stability and geometry. The picture wasn't just beautiful, it became a scientific standard. Hubble's high-resolution image also opened the door to far more detailed spectroscopy than ever before. Researchers could separate the light from the golden core and the blue ring, comparing their chemical makeup, stellar ages, and rotation speeds with unprecedented precision. That became the foundation for many of the discoveries we've talked about, from the surprising age differences in the stars, to the uniform metal content in the ring, to the puzzling rotation curve and the quiet hydrogen halo. In many ways, the 2002 image marked the start of the modern investigation into Hoag's object. Seen from a wider perspective, that moment also showed the power of observation itself. We had known about Hoag's object for more than 50 years, but only as a faint, blurry curiosity. Everything changed the instant we looked closely enough. What had been a rare but unremarkable entry in a catalog suddenly became a cosmic riddle, and a challenge to how we think galaxies are born. But beyond the science, the 2002 Hubble photo carried a deeper, almost emotional weight. It reminded us that the universe isn't always chaos and wreckage. Amid the cosmic violence of collisions and explosions, there can still be structures of perfect harmony, as if carefully placed. It showed the quiet power of simply looking, that when we observe with enough clarity, we can uncover masterpieces that were invisible before. For many space enthusiasts, seeing Hoag's object in Hubble's crisp detail was one of the clearest proofs of the universe's unpolished natural beauty. From that day forward, Hoag's object stopped being a forgotten oddity in the Galaxy catalog. It became an icon, challenging, mesmerizing, unforgettable. The 2002 image didn't just push science closer to an answer, it reignited wonder in anyone who gazes upward. In a world where so much has already been explained, there are still moments when the universe makes us stop and whisper, "Wow." Hubble's portrait of Hoag's object was one of those moments, where beauty and mystery met, and reminded us how much remains beyond our understanding. After all the data collected, the hypotheses proposed and then discarded, Hoag's object still lingers there, silent, suspended in the cosmic dark, a riddle with no solution. We've measured the ages of its stars, both in the core and in the ring. We've compared their chemical compositions, traced its rotation curve, modeled its dark matter halo, hunted for any hint of collisions or ancient gas streams. Yet the deeper we look, the stranger it becomes. Hoag's object seems to smile back at every human effort, like a grandmaster quietly guarding a secret move in a cosmic chess game billions of years long. What we know so far only makes its oddness stand out more. At the center lies a golden, aging elliptical galaxy, slow spinning, long past its era of star birth, stripped of gas and dust. Encircling it is a vibrant blue ring, young and full of life, brimming with newborn stars fueled by some mysterious source of gas. Between them is a perfect gap, a clean divide, as if the two realms have never touched. The whole structure is nearly flawless in symmetry, no scars, no distortions. Every standard theory of galaxy formation, violent mergers, bar resonances, cold gas accretion, stumbles when trying to explain such calm perfection. Its mystery runs deeper than shape. It's in the physics and chemistry. Two stellar populations coexist but remain separate, as though they belong to entirely different galaxies. Its dark matter halo refuses to follow the usual playbook, bending its rotation curve away from predictions. A massive hydrogen halo surrounds it, but sits eerily still, showing no sign of the energetic gas flows that could feed star formation. The young ring's metallicity is astonishingly uniform, hinting at some quiet, unseen mixing process never directly observed. And all of this happens in deep isolation. Hoag's object has no nearby neighbors to stir or feed it. In many ways, it's forcing astronomers to rethink the story we tell about how galaxies evolve. For decades, the dominant idea has been that galaxies grow through chaos, collisions, mergers, bursts of star formation, and violent streams of gas. Smash-ups have been seen as the engines of galactic transformation. But Hoag's object, with its serene balance, feels like a quiet counter-argument. It suggests there might be another path, one where a galaxy can reshape itself without upheaval, where matter can gather and arrange into elegant symmetry without violence. If that's true, it could open an entirely new field of study, the quiet evolution of galaxies, a process long overlooked because it's so hard to catch in action. Perhaps out in the lonely reaches of space, there are more Hoag-like galaxies, silently existing far from crowded clusters and cataclysmic crashes. They leave behind no obvious scars, no dazzling fireworks, and so they slip past our large surveys unnoticed. Yet, when we do spot them, they might force us to widen our theories of how galaxies can form and renew themselves. It's also possible that Hoag's object is pointing straight at something deeper. That dark matter, which makes up most of the universe's mass, yet remains elusive, plays a far more intricate role than our models assume. If its halo truly has an unusual structure, stable enough to hold a young stellar ring in place, to mix gas quietly, yet not obey the standard rotation curve, it could mean we're missing a key piece about gravity or dark matter itself. Many physicists now see Hoag's object as a natural laboratory to test bold ideas, even alternative theories like MUND. And while there's still no clear answer, Hoag's object has already done something important. It has sparked curiosity. It's driving better simulations, deeper observations, and more sensitive instruments in search of clues. It's inspiring young astronomers, reminding us that the universe is still full of surprises, and that not every question comes pre-packaged with an answer. In an era when we sometimes feel we've mapped the big picture of galactic origins and fate, Hoag's object quietly, but firmly, reminds us that we're still only scratching the surface. On a more human level, it also nudges us to think about beauty and order in the cosmos. We often assume order must emerge from chaos, but this galaxy seems born from an unusual calm. It's like a flower blooming in the desert of space, needing no storm to scatter its seeds. Its symmetry is both mesmerizing and challenging, making us wonder, is beauty just a cosmic accident, or does the universe have secret ways of weaving harmony we don't yet understand? Even if the answer is purely physical, the feeling of wonder it stirs is deeply human, the same feeling that made our ancestors look up at the night sky in awe. Perhaps Hoag's object's greatest gift is its very mystery. Science isn't just about answers. It's about finding questions so beautiful they pull us forward. This is one of those questions. It doesn't just challenge astrophysical models, it rekindles the desire to explore. In its silence, we hear a reminder. The universe is still vast and full of unknowns, and just when we think we've figured it out, somewhere a quiet galaxy is spinning, smiling, waiting for us to find it. And maybe that's the most beautiful message Hoag's object offers, that even in a universe of chaos, collisions, and violent processes, there are places of astonishing balance. Structures so elegant, they make us pause, stare, and admit that nature can craft beauty beyond imagination. It's proof that the cosmos isn't just a cold machine obeying equations, but also a hidden artist, sometimes leaving masterpieces that leave science stunned. And in searching for its secret, perhaps the most precious thing we'll find isn't a final answer, but the journey itself. A journey that reminds us there are still countless wonders waiting, just beyond the edge of our understanding.